So you want to learn machine learning in 2025. You've gone through all the online courses about coding, math, and whatever else you can find, but something's still not clicking. And that's because you've neglected the most important part: papers. But I've read so many papers, you might say, and that's a good start. But the real value of papers doesn't come from reading them. It comes from re-implementing them. You should know that ML engineers with paper implementation skills earn 24% higher salaries. And the best part of all, there's not that much for you to read through. Take a look at this. 3 foundational papers appear in 83% of ML interviews, which means if you read through and re-implement just 3 papers, you'll have hands-on knowledge for nearly every ML interview you'll ever get. The first paper, cited over 45,000 times, powers computer vision systems at Tesla, Google, and Apple. This is a goldmine, a practical roadmap for how this stuff works, whether you're a beginner or experienced developer. So let's take a look. Assuming you already have Python, NumPy, PyTorch, and math proficiency, you can get your start by re-implementing the revolutionary ResNet 5 paper, introduced by Jan LeCun in 1998, which pioneered the image recognition subfield. Its key innovation lies in the use of local receptive fields, shared weights, and spatial subsampling. This architecture efficiently handles shift, scale, and distortion variants in handwritten digit recognition. You'll see that the ResNet 5 architecture consists of 7 layers. It starts with an input layer for a 32 by 32 grayscale image. This feeds into the first convolutional layer, C1, which produces 6 feature maps. Next, you'll have a subsampling layer, S2, followed by another convolutional layer, C3, with 16 feature maps. Another subsampling layer, S4, precedes a fully connected layer, F5. Finally, you'll have an output layer with 10 classes, 1 for each digit. Your implementation begins with data preparation. You'll use the MNIST dataset as input, with images resized to 32 by 32 and normalized. This pre-processing ensures consistent input format and helps your model learn more effectively. Next, you should define your model using PyTorch. Your ResNet 5 class will mirror the original architecture, with convolutional layers, average pooling, and fully connected layers. The forward method you'll write defines how data flows through the network, applying the TON activation function between layers. For training, you'll use stochastic gradient descent with momentum as your optimizer. You'll iterate through epochs, feeding batches of data through the network, calculating loss, and adjusting weights through backpropagation. Here's a crucial detail. Speaking of, thanks so much for all the support on the channel lately. It really means a lot, and I want to give something back to you guys. So do you need a job? That sounded a bit weird. But whether you're a UX designer, app developer, freelancer, or just a curious viewer, I want to get to know you guys, share some UX and UI tips, and maybe even get a gig. So I made a Discord channel for us and want to make this the place to be for front-end professionals. And I'm having talks with people to get some employers in there so you can connect with them too and find some jobs in the future. I'm really excited to get this thing started, so I hope you'll join me. Stick to the TON activation function for authentic replication. Modern functions like ReLU, while powerful, weren't part of the original design. Also, ensure you've got correct input normalization. These details matter for accurately reproducing the paper's results. Now, let's shift your focus to Word2Vec, introduced by Mikolov et al. In 2013. This model transformed natural language processing by creating dense vector representations of words, learning word embeddings through context prediction. You'll focus on the skipgram architecture, which predicts context words given a target word. Your model will consist of an input layer for 1 hot encoded words, a hidden layer for the embedding dimension, and an output layer with a softmax over the vocabulary. Your data preparation will involve tokenizing a corpus and creating a vocabulary. You'll see NLTK for tokenization and create a mapping from words to indices. You'll define the skipgram model with an embedding layer and a linear layer. Your forward method will retrieve embeddings for input words and produce log probabilities for context words. To train this model, you'll need to employ negative sampling in order to handle larger vocabularies efficiently. You'll generate batches of context target pairs, feed them through your model, calculate loss, and update weights. You'll continue this process for several epochs. Watch out for this common pitfall: inefficient training on large vocabularies. You should use negative sampling or hierarchical softmax to significantly speed up training and allow your model to handle larger datasets. Finally, you'll tackle ResNet, introduced by He et al. In 2015. This model solved the vanishing gradient problem in very deep networks using residual connections. The key innovation you'll implement is skip connections that allow gradients to flow directly through the network. Your ResNet architecture will start with an initial convolutional layer, followed by multiple residual blocks. It'll end with global average pooling and a fully connected layer. This design allows you to create extremely deep networks without suffering from vanishing gradients. You'll begin by defining a residual block. Each block you create will contain 2 convolutional layers with batch normalization. The crucial element is the shortcut connection, which adds the input to the output of these convolutions. You'll then construct the full ResNet model using these blocks. You'll start with a convolutional layer, followed by multiple layers of residual blocks. Your network will end with an average pooling layer and a fully connected layer for classification. For training ResNet, use the Atom Optimizer. You'll iterate through epochs, feeding batches of data, calculating loss, and updating weights. The key to your ResNet's success will lie in its ability to train very deep networks effectively. A critical point: you must ensure the dimensions match when adding the residual to the convolution output. This is crucial for your model to learn effectively. These implementations you've worked through form the backbone of modern machine learning systems. ResNet 5 laid the groundwork for convolutional networks in computer vision, introducing you to local receptive fields and shared weights while demonstrating how neural networks could effectively tackle image recognition. Word2Vec revolutionized natural language processing by creating meaningful word representations without explicit supervision, enabling machines to grasp semantic relationships between words. ResNet pushed the boundaries of model capacity by solving the vanishing gradient problem through skip connections, proving that extremely deep networks could be trained effectively for more powerful and expressive models. Now, let's turn your attention to a more recent breakthrough: TimesNet. This paper will expand your toolkit beyond image and text processing, diving into the realm of time series analysis. TimesNet treats time series data as a 2D variation problem, a novel approach you'll find fascinating, instead of viewing time series as simple 1D sequences as done previously. This allows you to capture both short-term and long-term patterns more effectively than you could with traditional methods. You'll implement a combination of 2D dilated convolutions and self-attention mechanisms. This might sound complex, but you'll find it's a natural extension of the concepts you've already mastered in ResNet 5 and ResNet. As you build your TimesNet model, you'll see how it can handle both univariate and multivariate time series data. This flexibility will allow you to apply your model to diverse domains, from financial forecasting to healthcare monitoring and even industrial IoT applications. A key point to remember: pay close attention to how you reshape your time series data into 2D grids. The effectiveness of TimesNet heavily relies on this transformation, so you'll want to experiment with different grid sizes and reshaping strategies. By implementing TimesNet, you'll round out your understanding of how deep learning can be applied across different data types: images, text, and now time series. This comprehensive knowledge will set you apart in the rapidly evolving field of machine learning. By mastering these architectures, you've built a solid foundation for understanding and implementing cutting-edge machine learning models. Each paper you've worked through builds upon the last, showcasing the field's rapid evolution. By replicating these seminal works, you're not just learning individual models, but gaining insight into the thought processes driving innovation in machine learning. The skills you've developed in implementing these models will serve you well as you move to more advanced topics. You'll be able to read and understand new research papers, implement novel architectures, and perhaps contribute your own innovations to the field.